All right, in this video, we're going to look at one of the most important radical reactions, at least in the terms of synthetic organic chemistry, and that is radical halogenation. So in radical halogenation, we're adding a halogen atom to an alkane. And alkanes generally aren't very reactive, so this is a good way to introduce functional groups to an alkane. And so the first step in radical halogenation is an initiation step. Right, and so it's the creation of the halogen radicals. So we start with our halogen molecule, we hit that with a high energy photon, and then that creates two chlorine radicals. All right, following the initiation step, we have various propagation steps that are possible. Right, and so these steps are self-sustaining because as propagation steps, we're creating new radicals, which then go on to react with other things. And so in the first step of, or the first propagation step, right, we have a hydrogen abstraction. So the chlorine radical is stealing a hydrogen atom, but the other electron from the carbon-hydrogen bond forms a new radical on the alkane. The second step in, or the second propagation step in the radical halogenation mechanism is a halogen abstraction. So the new methyl radical that we created can encounter a Cl2 molecule, right, and then it can abstract one of the chlorine atoms, creating a new chlorine radical. They can go on to find another alkane and continue the reaction. And then following, or in addition to the propagation steps, termination steps are also possible, right? And so this sort of ends the reaction, if you will, right? And so all of the termination steps are different coupling reactions. And so if two chlorines find each other, right, we can reform a chlorine molecule. Or in this case, if one of the methyl radicals that we created finds another chlorine radical, we can get a coupling reaction there. So this sort of doesn't create any new radicals, but it does at least create the product. But then one thing that's common in radical reactions is we often get a lot of unwanted reactions. So it's also possible that if two methyl radicals find each other, we could get coupling between them to form a new alkane that we didn't necessarily want to form. And it's also true that, once I form this monohalogenated alkane, it's possible that this could react with other radicals to give us dihalogenated alkanes. And so there are a lot of side reactions and competing reactions that are possible. And so that can make radical halogenation sort of a messy process, but it's one of, or at least it's a good way to introduce functionality to alkanes that aren't very reactive otherwise. And so if I consider the two propagation steps, right, where we have the hydrogen abstraction first and then the halogen abstraction, if I sum these two steps together, it gives us the overall net reaction. Now, in the previous example, we just had methane, and so there was only one monohalogenation product possible. But if we have different types of hydrogens, then we can form multiple different products. For example, if we react propane with chlorine in a radical halogenation process, we can add the chlorine both here and here. And chlorine in particular is very reactive, and so it will often form all of the different possible products. Now, not all products are produced in equal amounts, and if you go back to the steps of the mechanism, the first propagation step is creating a radical on the alkane, and because a secondary radical is more stable than a primary radical, in this reaction we'll get more of the secondary alkyl halide than we do of the primary alkyl halide. Now, bromine is often more useful than chlorine because it's more selective. It's not as reactive. The reaction is a little bit slower, and so in this case we get much more of the more substituted alkyl halide. Because, again, right, the secondary radical is much more stable than the primary radical. And so bromine is, in some sense, more useful from a synthesis perspective because we're better able to control which product we get. And this is just another example to show the selectivity of bromine being much higher than chlorine. In the case of this compound, where we would form a tertiary radical or a primary radical, right? Chlorine sort of chlorinates everything, right? We do get mostly the tertiary alkyl halide, but we still get a lot of the primary alkyl halide. Whereas in the case of bromine, essentially we get all of the tertiary product and basically none of the primary product. All right, the last topic for this video is the stereochemistry of radical halogenation. In the previous video, we talked about the structure of radicals, and we said that they were basically trigonal planar. Sometimes they were sort of a shallow pyramid that rapidly inverts. In either case, the halogen is able to attack from either side in the second propagation step, and so we'll get both stereoisomers in the halogenation reaction. Right, so just an example. When we form a new chiral center as a result of the halogenation, we'll get both stereoisomers.